Hi there. So today we're going to be going over Taylor series and analytic functions. So before we get to what a Taylor series is and what an analytic function is, let's do a quick review of the idea of differentiability classes. So differentiability classes. Okay, so this should have been done last year, but let's just go over this again quickly. So the first class is called C0, and that is the set of continuous functions. Okay, then we have the set C1, which are the differentiable functions. Okay, so these are functions where you can take the derivative and the result is continuous. Okay, so we say that they belong to the set C1 because you can differentiate once. Then we have the set C2, and that is the set of twice differentiable functions. Okay, so this is the set of functions where you can differentiate the function twice and the result is continuous. Okay, we can extend this idea to the set CK, which are functions that are k times differentiable. Okay, so given a function from this set, you can differentiate k times and the final result will be continuous. We can extend this even further to the set called C infinity, and this will be new to you. This is the set of smooth functions. So that's the name for these. They are the smooth functions. And these you can differentiate as many times as you like. And the result is again continuous. So you can differentiate as many times as you like. And the result is continuous. Okay, so examples of smooth functions, those are polynomials. For example, if you have y equals x squared, you can differentiate once and you'll get 2x, differentiate again. Let's just write that down. So f of x equals x squared. You can differentiate once and you'll get 2x. Differentiate again, you'll get 2. Differentiate another time, you get 0. And the 0 function is differentiable. So you differentiate the 0 function, you get the 0 function back, and you can do this as many times as you like. Okay, so this example is just with x squared, but you could do this with any polynomial. Okay, and other examples include trig functions like sine x and cosine x, because they just turn into each other. So you differentiate sine, you get cosine, you differentiate cosine, you get minus sine, and it ends up just making a loop. Okay, so you can differentiate as many times as you like, and the result is continuous because sine and cosine are originally continuous. Okay, other functions, that's like e to the x, that's going to be smooth. 1 over x, that's also smooth. So you see there's quite a few examples of functions that are smooth, okay, or arbitrarily often differentiable. Okay, and we represent that by C infinity. Now, these sets are not separate sets. They are contained within other sets. So we start off with the set of continuous functions. That is the quote unquote biggest set. Okay, so we can have quite a lot of continuous functions, but if we add the condition that it needs to be differentiable, then we get a smaller set. So C1 is a subset of C0, and C2, that is an extra restriction, so that will make it a subset of C1. And we get this chain of subsets. So we have C0, you can think of that like the biggest set. Then if we add the restriction of being differentiable, it gets smaller. Sorry, that's C1, it gets smaller. Then we have C2, so, all the way down to CK. Okay, so we see the inclusions make the set smaller and smaller as we go down. And this is smaller all the way down until we get the smooth functions. That's, you can think of that as the smallest set because that has the largest restriction on those functions. However, that's not the end of this. Okay, it can go down further. But the one that we're going to be looking at is the so-called analytic function. So that's one step below smooth. We call that C omega. Okay, so we say that is the set of analytic functions. Okay, so what does that mean? So definition. A function f is said to be of class C omega or analytic. That's just the name. If f is smooth, okay, so it must belong to C infinity, but it's more than that. There's an extra restriction that makes it a part of C omega. So firstly, it must be smooth. And its Taylor series. Yeah, so its Taylor series expansion around any point, let's say P, in its domain, converges to the function around some neighborhood of that point P. Okay, so we've got a bit to unpack from this definition. So firstly, it gives us the name of the set, so C omega. Those functions are called analytic. Okay, so that's first. And secondly, we need to unpack this idea of Taylor series expansion. So what exactly is a Taylor series expansion? How do we find it? And what can we do with it? Okay, and thirdly, we need to look at this idea of converges to the function. So we've got this Taylor series. We'll see how to calculate it. But does the Taylor series converge to the function? If it does, then we say that the function is analytic around that point P. If it doesn't converge, then it is not analytic. Okay, so it gives us a way of identifying if a function is analytic or not. In other words, does it belong to that set or not? Okay, so first thing, what is a Taylor series expansion? Okay, so a Taylor series expansion is a way of writing a function let's say f, as an infinite polynomial. Okay, so what do I mean by an infinite polynomial? Well, I mean, we take this function f of x and we write it as the sum from k equals 0 to infinity. So we have an infinite number of terms, which makes the sum actually a series. So if there's a finite number of terms, we call it a sum. If there's an infinite number of terms, we call it a series. So this is a Taylor series because there's infinitely many terms. Okay, so we have this infinite series of a k x to the k. Okay, so it's an infinite polynomial. So we can write out a couple of these terms. It's going to be a0 plus a1x plus a2x squared plus and so on for infinitely many terms. And we see that this is a polynomial if we truncate at some point. So a0 plus a1x plus a2x squared, if we cut it off there, or we truncate it there, that's just going to be a quadratic polynomial. And then we add more and more terms. And then if we add infinitely many, we end up with this Taylor series. Now, the goal of finding the Taylor series is finding these coefficients, the a0, the a1, a2, up to infinity. So there's infinitely many coefficients to find. There are infinitely many coefficients to find. Okay, now this might seem impossible. How do we find infinitely many coefficients? But we'll see through these examples that there's actually a pattern with a0, a1, and a2. So we just need to find the pattern, and then that will give us all of these coefficients. Okay, now how do we find them? Well, first, let's not look at an infinite series first. Let's look at a finite truncation of the series, so just the finite number of terms, and we'll develop the method on how to find these coefficients. So let's look at a finite truncation of the series. Okay, so let's say we look at the first three terms. So f of x is only approximate if we only look at a finite number of terms. So we have a0 plus a1x plus a2x squared. Okay, so if we just leave it at that, this is a finite truncation, and so it's only an approximation. So I'll put the approximately equals. Okay, but later on I'm going to drop the equals, but just remember that it's only an approximation. Okay, maybe we can write this as p of x instead of f of x, okay, since it's a different function. Okay, but anyway, we've got an approximation here. So it's only an approximation. Because it's only a finite number of terms. Okay, so of course it's not going to be exactly the function because we're supposed to have infinitely many terms. If we only take a few of them, then it's going to be an approximation to the function. If we add more terms, it will be a better approximation, but still an approximation. So we call this a Taylor approximation. Yeah, in this case, since it's a quadratic or order 2 polynomial, this is a Taylor approximation of order 2. If we took more terms, then it would be a Taylor approximation of whatever the highest order is. Okay, so if you go up to x to the 4, then it's a fourth order Taylor approximation. Okay, but let's see, how do we find Yes, A0, A1, and A2. Well, if we let x equal 0, what do we get? Okay, so I'm going to let x be 0. Then we have that f of 0 is going to be A0. Okay, so I've just dropped the approximately equals, but remember it is an approximation. So f0 is A0 plus A1 times 0 plus A2 times 0 squared. But this just gives us A0. Okay, so that's how we can find A0. If we evaluate f at 0, that gives us our first thing that we're looking for, A0. Okay, what about A1? Well, to find that, let's consider f prime of x. So we take the derivative. Okay, no problem there. It's a quadratic. We know how to take the derivative. That's going to be A1 plus 2A2x. So A1 plus 2A2x. Now, if we evaluate this at 0, we're going to get A1 plus 2A2 times 0. But that's just going to be A1. So this is how we can find A1. We take the first derivative of the function, evaluate it at 0, and that gives us A1. What about A2? Well, consider the second derivative. That's going to be 2A2. If we evaluate this at 0, that's going to be 2A2. And that gives us a way of finding A2. A2 is going to be 1/2 f double prime at 0. So you see that we can find the next A term. So we have A0, A1, A2. We can find the next one by taking an appropriate number of derivatives and then setting the derivative equal to 0. In fact, there is a general way of finding the kth term if you repeat this procedure. So in general, we have that AK, so the kth one, is going to be 1 over k factorial times the kth derivative evaluated at 0. Okay, so why are we dividing by k factorial? This comes from the fact that we are using the power rule multiple times. So remember, for each use of the power rule, the exponent gets multiplied in front. So if we do it a bunch of times, that ends up giving us a factorial. So we divide by k factorial because of the repeated use of the power rule. And just as a little example to illustrate this, let's say we have f of x is equal to x to the 4. F prime of x is going to be 4 times x cubed. F double prime of x is going to be 4 times 3 times x squared. F triple prime is going to be 4 times 3 times 2 times x, and you see this continues. So the repeated action of the power rule builds up this factorial in front of the expression. Okay, and then after k uses of the power rule, we end up with a k factorial in front of x to the k. Okay, so then that gives us a nice expression for finding the kth coefficient that we needed. So we can put all of this together and finally write out the Taylor series expansion. So the Taylor series expansion of f and then we say about x equals 0. So that is the point at which we do the Taylor expansion, is given by, okay, so this is the special case when x equals 0, which is what we've been doing so far. We have f of x is equal to the sum from k equals 0 to infinity. Then we have ak, but ak is 1 over k factorial times the kth derivative of f evaluates at 0. So we can write that as the kth derivative of f evaluated at 0 over k factorial x to the k. And this is the expression we will use to find the Taylor series at x equals 0. Okay, that's the expansion point, because that's what we've been substituting into the derivative there. Now, if we wanted to do the Taylor series expansion around a different point, we would just need to shift everything over to that point. So if we want to find the Taylor series expansion around, let's say, x equals p, then we shift to that point. Okay, so the original one is at x equals 0. If we want to go to x equals p, we can just shift across. So now we have f of x is equal to the sum from k equals 0 to infinity, kth derivative evaluated at p, because we've got a new point that we're expanding about, over k factorial. And then we need to shift all the polynomial terms across to that point. But that's easy to do. That's just x minus p to the k. Okay, so it's very easy to just shift across to some other point that we're interested in. Okay, and just as a note with this, the special case of expanding around x equals 0, that gives this original case here. There's a special name for that, and that's called the Maclaurin expansion. So in general, we call it a Taylor series expansion. For the specific case that we looked at first, where we expand around x equals 0, that is the Maclaurin expansion. So the special case where we expand around x equals 0 is called the Maclaurin expansion. Okay, but in general, we call it a Taylor series expansion. Okay, let's have a look at some examples. Okay, so example number 1, the simplest example, that is f of x is equal to e to the x. Okay, this is a very simple introduction. Okay, so we start, f of x is equal to e to the x. So we need to evaluate the several derivatives at 0, and then that will help us find our ak terms. So f at 0, or the 0th derivative at 0, is going to be 1. Let's find the first derivative. That's going to be e to the x. The first derivative at 0, that's going to be 1. And this just continues exactly the same. So the kth derivative of this function is, again, e to the x. And the kth derivative evaluated at 0 is still 1. So all of those terms are going to be 1, which makes it very easy to write out this expression. So we have e to the x is equal to the sum from k equals 0 to infinity. The kth derivative evaluated at 0, but that's always going to be 1 over k factorial x to the k. Okay, and if you want to see a couple of these terms, we can write out a few. The 0th term is going to be 1. The first term is going to be x. Then we're going to have 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on. We have infinitely many terms for this expansion of e to the x. Okay, and just the note about convergence, you can check this, that if you substitute any value of x, the right-hand side, this infinite series, will will converge to the left-hand side. Okay, so we won't show this as a formal proof, but you can check. You won't need to check in the assessment, but you can check in principle that this right-hand side converges to the left-hand side. So that means e to the x is an analytic function everywhere because its Taylor series converges to that function. Okay, for this next example, we will see that it's only analytic in some places, not all over. Okay, so example 2. We have f of x is equal to 1 over 1 minus x. Okay, so you can check that this function is indeed smooth. We can take derivatives as many times as we like, which is good. That's what we need to do. So let's look at the 0th derivative. That's just the function itself. We need to evaluate this at 0. We're going to get 1 over 1. That's just 1. Okay, what about f prime? F prime is going to be minus 1 over 1 minus x squared, but we need to use the chain rule. That gives us another factor of minus 1, so that's a plus. We can evaluate this at 0, and that's going to be 1 over 1 minus 0. That's just going to be 1 again. Okay, so it looks very similar to what we had before, but don't jump to conclusions just yet. Let's have a look at some more derivatives. F double prime of x is going to be the derivative of what we did before. That's going to be minus 2 over 1 minus x cubed. And then again, the chain rule gives us another factor of minus 1. So we have a plus. Sorry, that's f prime. F double prime evaluated at 0. That's going to give us 2. Okay, so you see things are getting a bit more interesting now. Let's look at another one, the third derivative, 1, 2, 3. That's going to be 2 times minus 3, so that's going to be minus 6 over 1 minus x to the 4. Okay, and then we need to multiply again by the minus 1 because of the chain rule, so that's a plus. So the third derivative at 0, that's going to be 6. Okay, so let's do one more. So the fourth derivative is going to be 6 times 4, so that's going to be 24. Again, the chain rule makes it a plus, so we're going to have 24 over 1 minus x to the 5. The fourth derivative evaluated at 0, that's going to be 24. Okay, so what is the pattern here? Well, notice that each time we take the derivative, we are using the power rule. So remember what I said before, after multiple uses of the power rule, we end up with a factorial. So notice that the first term, the first one here, 1, we can write that as 0 factorial. F prime evaluated at 0, we can write that as 1 factorial. This next one we can write as 2 factorial. The next one we can write as 3 factorial. And the next one we can write as 4 factorial. So in general, the kth derivative of f evaluated at 0 is actually k factorial. So let's make a note. The kth derivative evaluated at 0 is k factorial. So that's the pattern that we wanted to find. So let's substitute that in and see what we get. So 1 over 1 minus x is equal to the sum from k equals 0 to infinity of the kth derivative evaluated at 0, but that's k factorial. Then we need to divide by k factorial and then times x to the k. Now, the k factorial at the top and the k factorial at the bottom, they're going to cancel. So we end up with the sum from k equals 0 to infinity of x to the k. So that's going to be 1 plus x squared plus x cubed plus dot, dot, dot. Infinitely many terms. Now, what about convergence? So if we substitute, let's say x equals 2, substitute x equals 2, then the left-hand side is going to be 1 over 1 minus 2. So that's going to be minus 1. What about the right-hand side? The right-hand side is going to be 1 plus 4 plus 8 plus, and so on. We're going to have infinitely many terms that are getting bigger and bigger and bigger. So in fact, the right-hand side diverges to infinity. So it does not converge. Okay, so you might recognize this series from high school. This is actually the geometric series. Okay, the 1 plus x squared plus x cubed, that's a geometric series. And we know that the geometric series converges if the ratio, or in this case x, the magnitude is less than 1. Okay, so for the right-hand side to be equal to the left-hand side, we need that the absolute value of x is less than 1. So this converges for absolute value of x being less than 1. If the absolute value of x is outside, or sorry, if x is outside this region, then the right-hand side goes off to infinity, whereas the left-hand side remains finite, and so there's this mismatch, and so it does not converge. Okay, so this function is analytic, but only on this domain here. Okay, so the previous example, that was analytic everywhere. You don't need to show that, but just take my word for it. Whereas this example, we can see immediately that this only converges for the absolute value of x being less than 1. Okay, because we recognize that this is a geometric series, and we know about the convergence of those. Okay, let's give you some homework to try. Okay, so homework. Okay, so find the Taylor expansions of sine x, cosine x, and the natural log of 1 plus x. Okay, so find the Taylor expansions of that. Okay, just one more thing before we stop with this Taylor expansion, and that's just a little interesting side note. If we take the Taylor expansion of certain functions and we let x be some fixed value, then we end up with an infinite series that converges to some value. So if we just look back here, sorry, at example 1. Okay, so what do I mean? Here we know that the right-hand side converges to the left-hand side for any value of x. So in fact, if we substitute x equals 1, so substitute x equals 1, then the left-hand side becomes e. So that's just Euler's number. And the right-hand side becomes 1 plus 1 plus 1 plus a half plus 1 over 3 factorial plus 1 over 4 factorial plus and so on. So just by substituting this value of x, we see that this Euler's number e can be written as an infinite series. So this infinite series converges to that number there. Okay, and we can do a similar thing here. So for this last homework problem, once you're done finding the Taylor expansion, substitute x equals 1 to find a series representation of the natural log of 2. So if you substitute x equals 1 on the right-hand side, you'll have an infinite series of terms. If you add all of them up, we get log 2. Okay, because we know that the right-hand side converges to the left-hand side. Okay, and I will post a couple more problems later on finding the Taylor expansion. And then by substituting different values of x, you can find interesting series representations of different numbers. Okay, so there's also a series representation for pi. Okay, so that is if you find the Taylor expansion of arctan of x, we'll cover that later. If you find the Taylor series expansion of that, you substitute a certain value of x, you can find the series expansion for pi. Okay, and other series expansions as well. Okay, but that will be done in the other homework problems. Okay, as always, if you have any questions, please email me or email the tutors. We'll be happy to help if you let us know. Okay, but give these problems a go, and I will post the homework, these homework problem solutions a bit later on.